Okay, everyone, so thank you for being with us tonight for this audio analytic tech talk. If my memory is correct, that's the fourth one in the series. So as you know, audio analytic is the lead provider of sound recognition technology, but something I very often repeat is that we don't believe in innovation in a box. We believe in connecting with brilliant researchers. We believe in connecting with people in that field and discussing ideas. So that we don't reinvent the wheel, we only invent what is necessary for this technology. So we've been lucky enough to have, for the past 3 editions, Mark Plumley, who gave a wide panorama of sound recognition research. Then we had Emmanuel Benetos, who focused more specifically into non-negative matrix factorization. And then we had Bob Sturm, who made a very interesting talk about evaluation of the systems and the pitfalls to avoid in machine learning in general, in a wide sense. So if you haven't been with us for these past tech talks, please have a look at them. They're on YouTube. The YouTube address to the videos is actually from our blog. The blog is labs.audioanalytic.com. So if you'd like to see the past tech talks, please visit labs.audioanalytic.com, and there is a link there to the past videos. So tonight, we're very lucky again to have a very prestigious guest with us. He traveled all the way from Finland, which we're really grateful about. He's the lead researcher of the audio research group of the Tampere University of Technology. Please give a big welcome to Tuomas Virtanen.
Thank you, Sasha, and welcome from my behalf as well. It's very nice to be in Cambridge. It's 10 years since the last time I was here as a fresh postdoc working in the Department of Engineering. Almost all my research career I've been developing methods and algorithms that analyze sounds. For example, speech recognition is one example that everybody knows, and which is working very well on your mobile phones now. And in this talk, I'll be focusing on machine listening of everyday environments. For example, street, cars passing by, footsteps, or home or office sounds in this environment. So there is relatively little research in long term on this topic. So speech recognition has been studied for decades, but this analysis of everyday environment is a rather new area with lots of interesting applications and at the same time research challenges. So if we pose a very high level goal to be able to automatically describe sounds in everyday environments, everyday environments, converting audio signal to some sort of description. How do we start tackling this problem? So first, in this talk, I will describe one concrete solution using sound event detection to describe everyday sound scenes. What are the scientific and technical challenges in this problem? And then basic supervised machine learning approach and the data that you need to do this kind of development. And then I will discuss in more detail various deep neural network-based approaches that have been used to obtain state-of-the-art results. I will compare a bit the different approaches and show some demonstrations. I will also discuss a public challenge that we are organizing this year related to this topic, if you are interested in participating. So when we do sound event detection, basically then we decompose this overall analysis of complex sound scenes into smaller problems. So we analyze sound scenes in terms of individual sound events that compose sound scenes. For example, car passing by could be one event, footsteps could be one, siren could be one. So this already makes this task much more concrete. And what is nice in this approach is that there is then methodology based on machine learning that we can use to do this kind of analysis, and it also already allows several applications. For example, that audio analytic is working on. So in sound event detection, what we do, we have an audio signal going as an input to a system, and then we estimate the start and end times of individual events, and then give some textual label to each of the events. And of course, these labels can be as detailed as your algorithm allows. So I'm now playing one example video. The descriptions here have been produced manually, so we are not quite there yet to produce this accurate description, but you can get some idea what kind of sounds you can find in everyday environment.
Morjesta. Joo, mä lähden tulemaan.
So sound events in everyday environments, they contain lots of information about the physical events that take place in that environment. And of course, that allows then lots of different applications. In this talk, I will be focusing on this basic methodology, not focusing on any specific application. But for those of you that haven't been working on this area, I will just mention a few applications so that you understand the potential of these methods. So for example, we can develop assistive technologies to visualize sounds for those that cannot hear them or those that cannot remember them. Some live log things, for example. And different kind of devices, robots, cars, mobile phones, can become aware of the environment. For example, if a car hears that there is children laughing from behind a corner, then that car could warn the driver or slow down automatically. Or the mobile phone can change the operation mode depending on the context. We can develop various kind of surveillance technologies, for example, if there is glass breaking or fire alarm like audio analytic is doing. And certain types of events like this can be very efficiently detected based on sound. And for example, in urban planning, city planners, they are interested in knowing in what kind of areas people spend their time and what they are doing. And information like this can be analyzed using sound. And similarly, we can develop tools for the biologists to analyze what kind of animals are present in a certain area, how many, what species. And we can do various kind of monitoring applications. For example, in urban areas, noise pollution is a big problem, and we can recognize noise sources and then design procedures to deal with those. And we can monitor faults in machinery, for example. And one very big application area is multimedia information retrieval. So there is lots of video in social media, and if you can automatically analyze its content, then you can do much efficient retrieval engines. Of course, there is lots of challenges also in this field. Everything doesn't work that easily. So if you consider everyday environments, there is lots of different types of sound sources with very different acoustic characteristics. So that makes the development of the methods so difficult. And even in one category of sounds, there can be big acoustic diversity. And in realistic environments, you have multiple sound sources which are overlapping. And for example, in this research field, what is different from, let's say, speech recognition is that typically then the sources that you are interested in are far away from the microphone. So there is lots of the signal that you can capture is highly reverberant. So all these factors together actually make this core detection problem really difficult. And also practical challenge is that there is no really established taxonomy to tell what are the possible labels for sounds. And in comparison to many other fields, then there is the amount of databases that can be used in the development is still rather limited. Okay, if we go then to more the methodology part, most powerful methods in this field, similar to many other fields, are based on machine learning, especially on supervised learning, which basically means that you have audio data, recordings of your target sounds, and then some labeling of those. So more concretely, what you can, for example, have if you have an audio signal, and then you can have annotations of that data, which basically tells when your target events are present in that audio. So the start time and end time, and you need lots of material like this. So let's say that in a simple detection task where your sound has quite prominent acoustic characteristics that are different from other sounds, then you can do maybe with tens of example sounds. But if you are developing a system to a scenario where there is several classes of sounds which can be highly similar, and there is some noises, then you may want to use hundreds or even thousands of examples. So actually obtaining suitable data becomes a very big part of the process of developing this kind of systems. So in this supervised machine learning approach, you need to define manually in advance what are the classes that you are aiming at. In the simplest case, you have a one target event versus all the other sounds, but you can be detecting multiple sounds also at the same time. So I will explain a bit the possible ways to obtain data when you start developing this kind of methods. So one way is to record audio from situations that are as close as possible to your end user scenario. Because in supervised classification approaches, this kind of matched condition when your training material and your actual usage case, when they are similar, then you can expect the best performance. So you can do audio recordings, or you can involve any users to contribute somehow by producing data and producing audio. But then you also need the annotations, which means markings of start and end times of the sound events. And this can be quite a slow and also uncertain process. So typically you want to involve expert listeners in doing this which makes it costly. On the other hand, you can also use synthetic material. So there can be some sample databases that contain examples of your target sounds. Or you can then record these individual sounds yourself. And then once you have obtained these samples, then you can produce some training material, for example, mixing your target events with some background with different impulse responses. And of course, this way you can produce large quantities of audio, and the annotations can be produced with some semi-automatic methods. If you do some synthesis of training material like this, then you have to be careful to verify that the system that you are developing then will work with real data as well. Because if your synthetic data is too artificial, does not really match with the actual usage case, then the machine learning approach will fail. So at least when you are testing your system, it's best to have some real recordings. So some examples of databases that we have collected in my group from the real audio category is this sound events database, TUT sound events database 2016 and 17. And the reason I'm presenting now this, that the 2016 database was used in this public D-case evaluation last year, and the 2017 version will be used this year. So they are kind of can be used as public benchmark datasets. So when we collected this data, we had a few different contexts. In this case, home, residential area, and street. So we had research assistants doing binaural recordings. So here the guy is wearing in-ear microphones, so which allows then a mobile recorder. So this allows him to do recordings in outdoor conditions pretty easily. And there is also he has also video camera on the chest, which can be used to help in the annotation process. So altogether, these databases contain about 4 hours of audio material. So of course, in comparison to some, for example, speech and video databases, this is quite limited. But this is anyway good starting point in our field. And this audio that was recorded was then manually annotated. So we annotated start and end times of sound events, and in the here we used a specific taxonomy for the sound event. So we annotated the sound production mechanism with a verb, and the sound source using a noun based on the WordNet taxonomy. And in order then to allow development and this public evaluation, we did some manual grouping of these labels to some classes, so that we have a reasonable number of sounds per each, sound examples per class. So altogether, there is then about 2,000 sound events annotated in these databases. And the 2016 database is available currently in this address, and the 2017 database will become publicly available in 1 or 2 weeks. And let me just play an example of material that is similar to these databases. This is not actually exactly from these 2 databases, but from a highly similar one, a project that we had earlier. So here we have this kind of event roll diagram. So if I now start playing this, so this is the current time, and active events are indicated with these blue bars. So there is some background traffic, and individual cars are on. Now you heard there was a car, and then soon another one is coming from there. And there's some brakes squeaking in the background. So material like this. And here in this example, the person doing the recording was moving. But now in this publicly available databases, we have stationary recordings, so one fixed location for each segment that is recording. So that's slightly different. I need to. Come on. I'm trying to go back to my slides. Yes. Some example of synthetic database. So, for example, recently, when we have been doing basic research on various neural network-based approaches, then we want to have large quantities of data, and that's why we created a synthetic database by combining individual samples from 16 classes like sirens, baby crying, bird singing, and so on. So we purchased samples from sound ideas, and we created about 9 hours of audio mixtures using those. And actually these mixtures are freely available for academic use from this web address. I will play a quick demonstration of this. So let me play the audio. Active events are indicated here, and these are the class names on the left. So this is highly unrealistic because the classes that are present together do not really have to do anything with each other, so they are totally random. But anyway, using this kind of material is useful when you benchmark your pattern classification algorithms. Okay, then to the actual methods. So I will discuss first this problem of overlapping sounds, how to deal with those, and then how to model the structure of the sounds with various deep neural network-based approaches. So first about overlapping sounds. So in realistic environments, for example, street, there can be lots of sound sources active simultaneously. And for example, in one of the databases from various different contexts, we had on average 2.5 sounds present concurrently. And now dealing with overlapping sounds is a big problem for many types of classifiers like GMMs, SVMs, because they are basically single label methods. Of course, what you can do is you can have a separate detector, completely independent classifier for each class. But then this kind of systems doesn't really model dependencies between sound events. You can do some source separation pre-processing to extract individual sources from the mixture, and this hasn't been done, and it works okay. Or then there are some NMF-based techniques, for example, which do some factorization of the mixture to directly obtain some classification of individual sources. This has been done, and it works also okay. But luckily then there is a very elegant solution, which is multilabel classification. Basically, which means that you are predicting the activity of all the classes at once. And so how it works is that you basically do classification in short audio frames. So this is this is this event activity indicator. So here goes time, and these bars indicate when each of the events are active. And you process the audio in short frames, let's say 50 milliseconds or something like this, and then you estimate which of the classes are active in one frame. So this is quite, if you formulate it like this is a multi-label classification problem. So this would be then your target vector in one frame. And what is nice with deep neural networks is that they allow very easy multi-label classification using this kind of one-hot encoding, where you have 1 to denote an active class and 0 to denote inactive class. And what is nice with deep neural networks that there is several different kinds of topologies that allow modeling the structure in audio. And nowadays there is also very good software libraries to allow training models so that you don't need to implement everything yourself. And of course, the DNNs are very popular in several neighboring fields, speech recognition, machine vision, and so you can borrow ideas from there and directly apply to sound event detection. So the basic way we can use DNNs for sound event detection works like this. First, the training part. So you have audio, lots of audio samples, and you have the annotation, which basically tells when each of the events is active. Then we do feature extraction from the audio. So typically this is done frame-wise. So in short blocks, you extract some vector of features. Some spectral features are typically used to produce some sort of a time frequency representation of the sound. So here is the time, and there is the feature vector per each frame. And then the annotations you just represent using this kind of multi-label encoding. So this is a binary matrix which tells when each of the event classes are active. And then you just learn a DNN to map your acoustic features to these class activities. And when you are using this system, you have some audio going into your system, you calculate the features, and you have the DNN which will produce you the probabilities of each of the classes. Then you may want to do some post-processing temporal filtering, and then you have to have some decision mechanism, some thresholding of the probabilities to get the binary estimates when each of the classes are active. So the basic setup is rather clear. Okay, for those of you that haven't been working with audio, some few words about the features. So typically we represent audio using some spectral features, because typically natural sound sources, their structure can be pretty well modeled in the spectral domain. Each source has some certain resonant structure, or there is some excitation signal with certain type of spectrum. So instead of the time domain signals, you, for example, represent the signal using energies in certain frequency bands. For example, MEL bands are quite commonly used. MEL resolution is something that is similar to the resolution used by the human ear. And for example, here I'm now visualizing the MEL spectrogram. So here you have the frequency bands, and there you have the time frames. And this is on the logarithmic, the intensities are converted to the logarithmic scale, because the dynamic range of natural sounds can be really large. So then taking the log of the intensities compresses the values and makes the distribution of the features more nice, and also makes the numeric range of the features more nice to work with. Okay, so now you have, for example, if you use log-mel energies, then the simplest approach that you can use to do sound event detection is feedforward neural networks. So in the simplest case, you are taking one frame of audio and then you have a feedforward neural network. So one block here illustrates one feedforward neural network to predict now the activities of your sound events. So those of you that are not familiar with neural networks, so this is a simple diagram of a feedforward neural network. So you have here the input nodes, which are the acoustic features, and then you have weighted connections from the input to some hidden units, and then there is some nonlinearity in these units, and the activations from this are then fed to the next layer of hidden units, and you can have arbitrary many of these hidden layers, and finally you have the output layer where you have the probabilities of your event classes. And well, with feedforward neural networks, you can already do pretty now sound event detection. The main shortcoming of them is that their capability to model the structure of sound, because in the case of sounds, for example, that modeling the temporal context is rather important. With the features that we have extracted, we can model the structure and frequency pretty nicely, but in sounds there is also the temporal structure that is highly important. And with the feedforward nets, what you can do, for example, is calculate features from multiple adjacent frames, combine multiple frames from multiple feature from multiple frames and concatenate them to one long vector, and that works. But if you want to model larger temporal context, then the amount of parameters, means the number of inputs to your system, becomes quite large, and then you need lots of training data to make this kind of system work well. So luckily there are then few better approaches to model the structure in sound. And one nice way to do is recurrent neural networks. So now this is an example, a recurrent neural network. And what we have here is two recurrent layers where we actually have connections between frames. So earlier, now in the case of feedforward, the processing was done independently for each frame. So you have just information flowing only in this direction. But now in the case of recurrent neural networks, you have connections from the past frames, and if your system is not online or causal, then you can have also this kind of backward connections. And this can model the temporal structure of sounds pretty nicely, even quite long-term temporal structure. With recurrent neural networks, then there are some numerical problems if you use this kind of vanilla recurrent networks, because when you propagate at the training stage, when you propagate the gradients through this network, then the gradients can either vanish or explode, which is problematic. And that's why in practice then the cells that are used in this recurrent layers are, for example, LSTM, long short-term memory cells, or GRU, gated recurrent units, which are elegant solutions to make this training work better. Then one other important tool in our toolkit is convolutional neural networks, which are basically time frequency filters that allow extracting some higher level features from your input features. So how CNNs work is you have a time frequency filters, like for example this square here is one filter, and then you convolve your input feature with space, which is over there, with this filter, and get one point to the next layer. And you move then this filter over the whole input space to get the number of points in this to this next layer. And you can have multiple filters to produce lots of these mappings. And you can have multiple of these layers. So the first convolutional layer doing convolutions on the input features. Then typically you want to do some max pooling, which is basically a way to reduce the number of parameters and also to make the representation invariant to certain shifts. Because here, actually, if you have multiple filters, the number of parameters that you have here is larger than in your input. And you can, by max pooling, actually you calculate some statistics over some processing blocks here over frequency, in this case, to make the number of parameters smaller. And also, when you do this max pooling over certain frequency, then basically you obtain a representation that is invariant to small shifts in frequency. And similarly, you can do this in time. What we are doing here is we don't do max pooling over time because we want to keep the original time resolution. And then after this max pooling, you can have other layer of convolutions, and you can repeat this several times. You can have many CNN layers. And for example, then we can visualize what do these CNN filters represent. So this is one study based on this synthetic data set that we used. So here what has been done, we were actually manipulating the input to the network to maximize the activity of some selected neurons of the networks. So if you maximize the activity of some selected neurons on the first layer, you can, for example, this kind of input would maximize it, which means that now that specific neuron that was chosen here reacts to some shapes like this, some blobs like this. Then in the case of this one, the neuron seems to react to some horizontal patterns. And in the case of this one here, it seems to react to some vertical patterns. So it seems that now then the individual neurons are learning some kind of core patterns, are learning to recognize some core patterns from the input. And then we can look at the higher layers. So then there is some other types of patterns. Here also some vertical lines, and this is some diagonal shapes. So basically, by having multiple CNN layers, you should be able to learn more complex and complex structures in the input. And then we can combine CNNs and RNNs to make, this is a figure of a complete sound event detection system that, which is basically the state of the art from my group. So we have the input, then a few CNN layers that I explained to you, and then we can have a recurrent layer which then one or more recurrent layers that allow longer term temporal processing. And then we can have a feedforward network to do some dimensional mapping from the recurrent layer to our target number of classes, and then some simple thresholding to get event activity predictions. So some details now about this complete system that I'm illustrating here: acoustic features, number of layers and neurons, and some training criteria. So as acoustic features, we typically use logomel energies. So those would be usually your starting point. Whatever is your analysis problem, then I recommend using logomel energies. Of course, if you have highly specific detection problem, then you can design some other types of features. Then in the neural network, we have used from 1 to 4 convolutional layers and from 1 to 3 recurrent layers. And about 100 or 250 neurons or filters per each layer. And like I said, we are using only frequency max pooling because we want to keep the temporal resolution accurate. In CNN layers, the rectified linear unit produces usually the best result. And in the recurrent layers, we are using GRUs. We are also using dropout, which is a good way to regularize your training. Dropout is basically randomly cutting some connections from your network, which makes it avoids overfitting to the training data. And the actual detection we are doing a very simple way. I guess this can still be improved, but we are just thresholding the network output at 0.5. As the loss function, we are using cross entropy, which is the default for multilabel, and Adam optimizer is very efficient. And we are using publicly available libraries, so Keras for Python and Theano backend. And when you have lots of amounts of data, then you want to use some clusters or GPUs. Okay, then some results that we get from different systems. So these are now with this synthetic database that I explained to you earlier. So if you have a binary GMM classifier, separate classifier for each class, then you get about 40% F-score. Then with feedforward neural networks, you can improve this pretty nicely to about 50%. With CNNs, you can improve that slightly by 3%. And with RNNs, using recurrent layers only, it's actually about 10% better than feedforward networks. So that's quite a nice improvement. But then by combining convolutional and recurrent neurons, then you get the best performance, about 66% F-score. And maybe at this point I will show, okay, first demonstration of the results. So this is the sample I played to you earlier, and now these are the results obtained by different methods. So the cRNN seems to obtain detection that matches almost perfectly with the ground truth. Okay. It's not playing for some reason. Okay. We will not have audio this time, but you heard the sample earlier and saw the annotations, and now you can compare. For example, the RNN is producing pretty continuous activation, so that's pretty good. So it's able to model the structure of the sound, but it's also making false detections like this one over here. And this might be interesting for many of you. So this shows the number of parameters of the system versus the accuracy. Here you can see that the cRNN can obtain very high accuracy with a relatively small number of parameters, whereas, for example, with RNNs, with the same number of parameters, you are much lower and you need more parameters to reach the highest F-scores. So what is good in CNNs is their compactness. So the amount of parameters in those filters is not that much. Okay, then some summary of these methods and applications. So sound event detection is a rather new research field with lots of new applications and also technical challenges. And multiple label neural networks provide at the moment state-of-the-art and also very good way to model the structure in sound and overlap in sounds. And you can have recurrent neurons or convolutional layers they are nice tools that enable learning high-level representations from training data automatically and also modeling long-term temporal structure. And you can borrow lots of ideas from automatic speech recognition and machine vision, which allows pretty rapid development in this area. And if I was now able to make you interested in this, okay, there are a few references over there. So this paper over here is our most recent one. So that contains the CRNN description details. So it's available in archive. So please have a look. And if you are now, okay, I would like to thank several people from my group who have contributed, who have actually done most of the engineering work behind these results. And now, if I was able to make you interested, I encourage you to participate in this public DCase evaluation this year. So we will have there 4 tasks. First task is related to skin classification, which is more traditional supervised classification problem. So that doesn't include temporal detection. Then we have an event on detection of rare events, which combines some synthetic audio overlaid with target events. Then we have a real-life audio detection problem using the type of material I was explaining. And then we have a large-scale weakly supervised sound event detection problem. Weakly labeled meaning that you have uncertainty about the temporal annotations, and a large scale by meaning you have lots of data. And we are going to release the challenge data in 1 or 2 weeks. Then submission deadline for your results and also papers is in June. Results will come in September, and in November we are organizing a workshop related to this in Munich. So this will be the website of this challenge. It's at the moment, I don't think it's yet open, but we are trying to make it open tomorrow or later this week. So please have a look. Thank you.